For those of you that didn't see it, there was an email sent out by Alice, one of the TAs, yesterday saying homework 7s were graded and uploaded. But basically she downloaded the submissions in order to grade them. Those that didn't have a name on them, she wasn't able to figure out whose they were. So if you see that you don't have a grade on homework 7, but you turned it in, just please email Alice or me the scan file that you submitted for your homework so she can match up whose is whose. There are a couple of people left. All right, so we're going to recommence with the last. Today's going to be the last of it's not even really new material. We already covered it last lecture, but the last real content, and then we're going to be into just examples, work problems, kind of wrapping things up in review. I do plan to post a practice final exam sometime in the next 24 hours. I'll also be holding a review session either like Sunday night or Monday night. Similar format to previous ones we've had. So stay tuned for more info on that. Okay. So we left off last time, right? Someone moved our projector. I don't know of an easy way to fix that. Let's see. Too far? All right, hold on. Perfect. All right, we'll do that. Okay. So we left off last time talking about the move from like a single surface that's radiating energy and getting irradiated with energy to what happens when you've got two surfaces. And I sort of breezed through something so I could give you some results. We're going to go back and cover that material so that we can finally wrap this topic up. So let's imagine that we've got two surfaces that are adjacent to one another. We'll call this one 1, and we'll call this one 2. And in between them, as I said, we have something that we call a non-participating medium. Now, technically, a non-participating medium means something that's not going to interfere with the transfer of radiated energy. So, technically, the only thing we really would use here is like vacuum or rarefied gas. But when surfaces are fairly close to one another, air can be approximated as a non-participating medium. So, we're not going to worry about the absorption of radiation by fluids. So the question is, all right, these are some temperatures. We'll say this temperature or this surface over here has an emissivity of epsilon 1 and absorptivity of alpha 1. This guy is epsilon 2, absorptivity 2, and then this guy will say they're both uniform temperatures, T1 and T2. So if we wanted to figure out how much heat transfer is occurring from one to the other by action of radiation, we sort of have to rewind back to where we started this whole journey. First law, right? A surface energy balance. So if we were to draw a control volume around this surface, okay? Next thing we want to do is we want to count up the radiation energy that's entering and that's incident upon and leaving from this surface, so we can figure out what the net radiative heat flux were. Remember, there were 3 or 4 heat fluxes we talked about. There was E. There was E. There was G. There was J, and there's Q double prime. E is emissive power. G is irradiation. J is radiosity, that is the emissive power plus the reflected portion of the irradiation. And Q double prime is basically the net amount of heat transfer, however much more energy is being radiated outward than is incident upon the body. And so Q double prime due to radiation, we would say, is equal to J minus G. So if we wanted to figure out what Q of surface 1 is, that is the heat transfer out of surface 1, we would say this is equal to A1 times Q double prime 1, or A1 times J1 minus G1, where J1 is equal to the emissive power, except for 1, plus the reflected portion of the irradiation. Okay. So this is right here is why this is going to become a bit of a headache, is because we've got G1 showing up in two places. If we wanted to write G1, the issue is that we've got G1 is essentially equal to A1, or this is equal to the heat transfer from 1 to itself plus the heat transfer from 2 to 1. There we go. G1 times A1. So, right, total energy flux in times the area gives us the total heat rate that's incident upon surface 1. And that heat, that thermal energy has to either come from itself, if it has a non-zero view factor, or it has to come from surface 2. So then, okay, if we continued sort of expanding these terms out, we would end up with that the heat transfer from 1 to itself is the radiated energy, well, it'd be J1 times A1 times F11 plus J2 times A2 times F21. And then we'd have to go and plug in values for J again. We'd say that then this expands out into epsilon 1 times the black body radiation of 1 plus the reflected irradiation of 1 plus epsilon 2, 2. All right, so it's all bookkeeping, and hopefully none of this, we can see this is getting increasingly messy. Okay, but hopefully none of it is like that crazy looking. Essentially, if we look through each term, we can figure out what it's saying. We're saying that all of the radiation that's incident on surface 1 has to either come from the active emission from surface 1 or the energy that's being bounced off of surface 1 transferred back to itself by this view factor. Or it has to come from the active emission or reflected radiation from 2 times the view factor from 2 to 1. So if we plugged all of these in, right, what we'd end up with is this growing sort of energy balance. And the problem is, right, we started this out, we said, all right, Q1 out is equal to this. We said we don't know what J is, let's write J out. We got something in terms of G, started writing something out in terms of G, and we got more G's, like gremlins. They keep multiplying. Right. So the problem here is that we can see we're not getting anywhere in terms of trying to solve for G1. We have more unknowns than we've got equations at the moment. So two ways of dealing with this. Okay, if we have to make some sort of concessions to the theory generally. Either we say the surfaces are black bodies, in which case we get to cancel a bunch of stuff out. So the problem is too many unknowns. Option 1, approximate as black bodies, both surfaces, okay, surface 1 and surface 2. And if we do that, then we end up with, right, Q1, we'd say that rho 1 is equal to rho 2 is equal to 0. That is, there's no reflection off of black bodies. They absorb everything. Alpha 1 equals alpha 2 is equal to 0. And epsilon 1 is equal to epsilon 2 is equal to 1. They're perfect emitters. Okay. Now I should mention that when I say option 1, okay, this isn't something you should just blithely choose to do if you have a heat transfer problem involving multiple surfaces. Simply saying I'm going to treat them as black bodies isn't usually recommended, because black bodies aren't, it's not a good approximation for something that's made out of wood or made out of metal. But if you're told, treat this as a black body, okay, then these are the steps you get to use in order to simplify the problem. So in that case, we'd say that Q1, right, is equal to A1 1 plus rho G1. Right, so we're back up here at this energy balance right here, okay? Where this right here is our, this right here is our J. But now we get to kill that term off because the reflectivity of a black body is 0. We would say this is equal to A1 times EB1 that's G1. Okay, I've added this EB1 because the implication here is that the emissivity, if it's a black body, is just equal to the black body emissivity, or emissive power. So I'm implicitly invoking this relationship right here. Okay, now if we tried to solve for G1 so that we can, we can express that hopefully in terms of some stuff that we actually know, we can say G1 is equal to, right, the black body radiation from 1 times the view factor from 1 to itself plus the black body radiation from 2 times the view factor from 2 to 1. Okay, what we managed to do here was we just took that relationship up there. Okay, this guy, we said that this is equal to 1, that goes away, this is equal to 1, that goes away. And now at this point, everything, we could plug G1 in here, okay, and everything is written in terms of black body radiation. So we could go ahead now and say that Q1, that is the heat transfer out of 1, that heat rate, is equal to A1 times black body radiation from 1 minus A1 EB1 from 1 minus A2 EB2 F21. And then finally we could substitute in the Stefan-Boltzmann law for these black body radiation terms, and we could say this is equal to A1 sigma T1 to the 4th minus A1 sigma T1 to the 4th F11 minus A2 sigma T2 to the 4th F21. Okay. That was a lot of work just to get one heat transfer rate out. But what I want to say here is what we've managed to do is take the problem where clearly it was cascading and kind of going into a tailspin, and by assuming black body radiation, we were able to boil everything down into terms that we should be able to know or figure out. Okay. Generally, you'll be given temperatures. So T1 and T2, those are known. Sigma, that's known. Areas, generally you'll know that going in. And then these view factors, F11 and F21, we don't know those yet, but we talked last time about how to use those tables to look them up. Okay, so these are terms that we can get. And so the beauty of this is now we know the total radiation out of surface 1. If we wanted to figure out how much radiation is going from surface 1 to 2, we would simply say, right, Q1 to 2 is equal to Q1 times F12. And there we go. We've got the radiation heat transfer from 1 to 2. And so we've solved the problem. We can figure out then also like the heat transfer from, we could do the same process from the perspective of surface 2, and we could solve for the heat rate from surface 2 to surface 1, etc. So that's what happens if the surfaces act as black bodies. Okay, we end up with this relationship here. However, what's more common is that these surfaces will decide that they form something that looks like an enclosure. Remember, the enclosure is any interior volume that's bounded on all sides. So option 2 here is basically if surfaces form an enclosure. And then this one has a couple of limiting assumptions here. And those surfaces are diffuse, gray, and isothermal, right? So if they emit and scatter radiation in all directions, if the definition of a gray surface is one, so basically here, E and rho G, diffuse, that's what that one means. Gray means that alpha and epsilon are independent of lambda, and therefore, by sort of the theory we talked about on Friday, right? We can say that alpha is equal to epsilon. And then isothermal, right? This just means that T1, T2, T, whatever, are constant. So each surface has just exactly one temperature that we have to worry about. Okay. So under these assumptions, what we can do is we could go back and we could start off our energy balance the same way we did previously. We could say, do that bookkeeping. We could say energy out, reflected radiation, plus emissive power. Okay. Energy in, irradiation from all other surfaces. And so you set that energy balance up for each surface. And what you should be able to do with this assumption, with these assumptions, is particularly this one, allows you to knock some terms out so that you get a system of equations that you can actually solve. So we're not gonna write this out, but you can set up system of equations to solve for J from, well, usually it'll be solving for J and G from each surface in the enclosure, and then from J and G, if you know J and G, then you can get and then you can infer what E is if you want that. So the only one that we want to, so the easiest version of an enclosure, this option 2 of a gray diffuse isothermal enclosure, is what we talked about at the very end of last lecture. This thing called a two-surface enclosure. So if we assume that here's one of our surfaces, here's our other surface. Okay, so we've got 1, we've got 2. Then the beauty of this is we say that, right, any energy transfer out of 1, the net energy rate out of 1, that is, that it doesn't count energy that leaves 1 and gets reabsorbed back into itself, because that cancels out in the energy balance. But the net energy out of 1 has to go to 2, right? And therefore it has to equal the negative of the net energy out of 2. This is a really powerful assumption because it cuts down on the number of unknowns in our problems, right? We also know that F11 plus F12 is equal to 1. We know that F21 plus F22 are equal to 1. So as soon as you know one of these terms, okay, then you can use reciprocity. So let's say we get F11 out of the book. We use reciprocity to get let's say we get F21 out of the book. We use reciprocity to get F12. We use summation rule to get F11, and similarly we use the summation rule to get F22. So we've knocked out some more unknowns right there. And in general, right, the two surface enclosure like this is actually so simple that system of equations, you can find the solution written out in the book, and it'll say that at Q12, that is the heat transfer out of Q1 to the negative heat transfer out of Q2 is equal to sigma T1 to the 4th minus T2 to the 4th 1 minus epsilon 1 for epsilon 1 A1 plus 1 over A1 F12 A2. Solution for heat rate in A2 surface enclosure. All right. Okay, so let's and that's basically where we're gonna this is the last new equation I'm gonna give you. So let's put this into practice, right? Last time I said the simplest version and the version of this that you have on the homework, right, was one where you've got two window panes, and you approximate that as a two-surface enclosure with the added simplicity that A1 is equal to A2, and that F12, because they're flat surfaces, basically F11 and F22 have to equal 0. So F12 and F21, respectively, are both equal to 1. So that further simplifies what's going on in this equation, and you end up with a really simple version of this equation that can be found in, I forget the table number, but I showed it to you at the end of last lecture. So let's do a very similar example to that last one that's on the homework. Let's assume we have two flat parallel surfaces that describe this is this is the wall cavity of a house with an area of 6 meters by 3 meters, 18 square meters. So this might be the wall of your living room, and we'll say that surface 1, this is, inside the house. And then here's outside. We'll say the surface 1 here is gypsum or drywall, which has an emissivity of 0.95 and is at a temperature of 295 Kelvin. Okay, they're keeping it pretty toasty indoors. This outside surface, we're going to say, is made of one of two things. So the idea is, right, here's the inside, here are all the people happily running their gas heaters. We'll pretend that this is 5 minutes ago and it's still freezing cold outside. And in here, we'll assume that this is some old house that doesn't have any insulation, okay, in between the inner and outer walls. So outside will be at 273 Kelvin, so it's right at freezing temperature. And this outside material is either going to be wood siding, which has an emissivity of about 0.8, or it's going to be Tyvek. Okay, this is that emissivity of about 0.1. Tyvek, right, is that sort of paper sheeting stuff that you'll see wrapped around buildings before they slap siding up. Okay, acts as a moisture barrier, and as we'll see here in a second, a good radiation barrier as well. So the question is, how much heat are we losing through this wall if we have just slapped up wood siding, or if we were to put a paper-thin sheet of Tyvek in between this wall cavity and the outside wall? Okay. So if we were to look at, there we go, table 13.3 in the book, and I forgot to bring my copy of the book with me today. But if we were looking at table 13.3, we would see that that's got solutions, right? It's got those Q12 rates for a variety of different two-surface enclosures. And the first one we find is two parallel surfaces. So from table 13.3, with A1 is equal to A2 is equal to A, that is saying that the surface area of the inside wall is equal to the outside wall. We would find that Q12 simplifies to A times sigma T1 to the fourth minus T2 to the fourth 1 minus epsilon 1 over epsilon 2 minus 1. Okay, so that's straight out of table 13.3. And what we find is that this is really simple. We have A, we know sigma, we're given the temperatures T1, T2. We'll go ahead and assume that the inside and outside walls are at thermal equilibrium, so that T1 and T2 are essentially they're steady state, and so T1 and T2 are approximately 295 Kelvin and 273 Kelvin, respectively. Okay. So, and then if we have emissivity 1, right? Here's emissivity 1, emissivity 2, or emissivity, we'll say 2A here. Then we could just plug those in, right? It's just a matter of crunching some numbers with the calculator. And so what we'd find is that plugging in, right, A, sigma, T1, T2, and epsilon 1, none of these change with this idea of using the wood siding versus Tyvek siding, or Tyvek wrap. Only the epsilon 2 changes. And so we plug in those two values, we'd find that for the wood siding, we get 1.582 kilowatts. With this Tyvek wrap in place, that drops to 205 watts. Okay, so this is This is here to demonstrate. This is neglecting conduction, neglecting convection. Right? This is purely radiation. But the idea here is, right, if you have a gypsum inner wall, drywall, and wood siding, because this emissivity is pretty high, you're essentially guaranteeing that you're going to be losing quite a bit of heat through radiation alone, plus that due to convection, plus that due to conduction. All right, and the remarkable thing is just by adjusting the emissivity of one of those surfaces, okay, and using something that's this paper thin sheet, we end up with cutting that number down by about 80%, 85%. All right. Yeah.
Would you ever be asked to solve for wood siding and pilot, like a wood siding pilot graph?
Nope. We're that would be the next thing in chapter, but you'll cover that in intermediate heat transfer if you do that. So it's called a radiation shield, and it's basically solving this two surface problem in series. Setting up two of those together. So it's really not too difficult, but I'm not going to expect you to do that. Okay. Let's try our hand at another one. Let's say we've got a triangular enclosure. Okay, we'll call this surface 1, this surface 2, and this surface 3. Surface 1 is 2 meters wide. In this case, we're going to assume all surfaces to be black bodies. Okay. So when they tell you to assume a surface or treat a surface as black, that's all that means. It said it has the properties of a black body. We're given that T1 is equal to 500 Kelvin, so that's this lower boundary here. T2 is equal to 300 Kelvin, and T3 is likewise equal to 300 Kelvin. All right. What we want to find is the heat dissipation rate from surface 1 per unit depth. That is, right, this is a two-dimensional sketch, and we've given you the width, but per unit depth into the page. So as with most of the problems we've worked, we're going to start out with our energy balance. So set up our surface energy balance, like so. We'll go ahead and sketch a control volume around this surface, and then start figuring out what the bookkeeping here looks like. So we know that right, there's going to be transfer of energy out from Q from 1 to 3 and from 1 to 2. All right. We don't know how much yet, but we know that there's going to be some. Likewise, we know that there's going to be energy transfer in from 2 to 1, Q, 3 to 1. So notice I haven't written anything yet about how much of this is irradiation versus emissive power. radiosity. This isn't yet in terms of E, G, J. Instead, this is being written more in terms of, we're talking about bulk amounts of power. And then we're going to figure out how much each of these is by writing them in terms of those individual radiative fluxes. So Q1, that is the net heat rate out of 1. We'll just go ahead and say this is Q1 to 2 plus Q1 to 3 minus Q2 to 1 minus Q3 to 1. All right. This is also equal to, and this is where we start writing things out in terms of radiation flux, A1 times the black body radiation of 1 times emissivity minus the absorptivity 1 times A1 times G1. Okay. This is equal to 1. This is equal to 1. Another thing I want to point out, right? When I was doing this similar energy balance up in the notes a little bit, I wrote it with rho instead of alpha, right? The difference there, right? They're equivalent. There are two ways of writing it. We're just saying we know that basically alpha plus rho is equal to 1. And so I have a choice. I can either say that rho, the reflectivity times G goes into the column of energy heading out, and that the energy coming in is basically is all of it, all of the energy that, or I can recognize that the energy, all of the energy coming out, G, minus the energy being reflected is equal to the energy being absorbed. So 6 of one, half dozen of the other. But I'll do it in both ways, so you see that the two are equivalent here. G1 times A1, right, is equal to Q21 plus Q31. So, right, we've said here is here's all the energy going out, the stuff that's written in red. Here's all the energy coming in. Then we're solving for the G1 times A1 term. That is everything that's composed of these two quantities. Q21 and Q31, right? We can also write in terms of these radiation, this radiation terminology. This would be A2, J2, F21 plus A3, J3, F31. Expanding J out, right, this is where things get fun. A2, we'll go ahead and move the F21 out here. This would be epsilon 2 B2 plus rho 2 G2 A3 F31 times epsilon 3 EB3 plus rho 3 G3. Okay. So this counts up all the different radiation terms that are throwing thermal energy at 1 from surfaces 2 and 3. Let me go ahead and I'll try to keep a little sketch going here. We've got 1. Which one was which? There we go. 2 and 3. Okay, but once again, because we're assuming that they're all black bodies, we get to say this is equal to 0, this is equal to 0, this is equal to 1, this is equal to 1, and so this boils down to A2, F2, 1, EB2 plus A3, F3, 1, EB3. Okay, so if we if we plug those back into this expression right here, okay, we've got our G1 times A1, then basically what we get is A1 EB1 minus A2 F2 1 EB2 minus A3 F3 1 EB3, or A1 sigma T1 to the fourth minus A2 sigma T2 to the fourth F2 1 minus A3 sigma T3 to the fourth F3 1. All right. What do we want to do now? Okay, we A1, A2, A3, those are pretty easy to find. Okay, our unknowns here, right, the things that are stopping us from just plugging in numbers here and crunching away on our TI-86s is F21 and F31 terms, right, the view factors. So like I said before, we set the problem up in such a way that if we find the view factors, then we're able to solve the problem. So we're kind of decoupling it. Okay, the view factors we can find, it's again using, in some cases, those tables in the book in chapter 13, or more simplistically here, we can use them by just sort of thinking about those rules that we set up before that govern view factors. For example, the summation rule and the symmetry rule together can be used here. So we say that and this looks a lot like the example we did with view factors last time, right? The summation rule would say that F12 plus F13 equal to 1. And the symmetry rule would say that F12 equal to F13. And so from these two, we say that F12 equal to F13 is equal to 0.5. Okay. Everyone with me there? The idea is, if this is 1, we're finding the view factors from 1 to each of these surfaces. Because it's an enclosure, they all have to sum to 1. And because it's symmetric, we know that the view factor for surfaces 2 and 3 must equal one another. Then we've got the reciprocity rule that we'll use in 2 ways. First, we'd say that A2 F21 is equal to A1 F12. We say that A3 F31 is equal to A1 F13, which is equal to, right, A1 over 2 and A1 over 2, because we've got that F12 and F13 are both equal to 1. Cool. Well, this is helpful because A2 times F21, A2 times F21, A3 times F31, A3 times F31, right? We've got some terms there that now we can substitute in. And so if we take this guy and respectively substitute them into this term, and that's backwards. Respectively substitute them into these 2 terms. And what we can do is we can write Q1 now is equal to A1 times sigma T1 to the fourth minus A1 over 2 times sigma T2 to the fourth minus A1 over 2 sigma T3 to the fourth. Now it's super easy to solve for Q. Okay. We can factor out A1, and we can essentially write this now as Q1 is equal to A1 sigma T1 to fourth minus 0.5 T2 to the fourth minus 0.5 T3 to the fourth. So if we plug in that following equations, we say that A1 is equal to 2 meters times B. We say that T1 is equal to our 500 Kelvin. We have that T2 and T3 are both equal to 300 Kelvin. And of course, our Stefan-Boltzmann constant, 5.67 times 10 to the negative 8th watts per meter squared, Kelvin to the fourth. We'll end up with Q1 equal to 6,169 watts per meter times B. So Q1 over B, that is the heat transfer rate per unit depth into the page, just works out to 6,169 watts per meter, and we're done. So that was pretty fast-paced. I hope that you guys were able to keep up. Any last questions you want me to kind of go back and cover on this before we call it an hour? Okay. Well then, we'll see you guys on Friday for some more review. And as I said, stay tuned for the information on the review session and practice exam.